I'm Fabrizio Pacini, and I'm an account manager at Terra2, and currently I'm also the project manager of the GeoHazard. Terra2 is a spin-off of the European Space Agency, founded in 2006 with the course in Rome. And from the first day, our mission is to provide support to researchers in earth science to use satellite geodata as information source in a collaborative environment. And for this, we provide a cloud platform to support our users to transfer in production scalable software application. With our platform, we have supported since the beginning the European Space Agency to develop the thematic exploration platform that is a set of R&D activities started in 2016 to demonstrate the benefits of new techniques for large-scale on-demand processing of geodata. And in that context, we have developed the GeoHazard exploitation platform, that is a platform based on virtualization and federation of geodata. Virtualization because it provides seamless access to cloud resources from private and public clouds, and federation of geodata because the GEP has access to more than 70 terabytes of ERS and MVSAT archive data, and to the Copernicus Sentinel-1, 2, and 3 mission available online. And also this offer is complemented by third-party missions like Cosmos SkyMed, SPOT, Pleiad, Landsat 8 and 9. And this is continuously growing due to cooperation and collaboration we do with parties like SEOS, the GeoHazard SuperSite National Laboratories, EPOS, and so on. Since 2018, we operate the GEP, and we are supported in this by our service providers that are recognized experts from the European Earth observation sector, and they expose their services on the platform. So relevant examples are CNRS EOS, the University of Thessaloniki, CNR IREA, and so on. The primary focus of the GEP is mapping hazard-prone land surfaces and monitoring terrain deformation. And the GEP supports the user community with both on-demand processing for specific user needs. On-demand processing meaning the processing that user can do by accessing our web interface and selecting parameter and launching job, but also the GEP is able to provide systematic processing where there is the need to address a specific analysis of large area of interest. Okay, just to give you some numbers and statistics from here 2022. Last year, at the end of last year, we had about 200,000 processing CPU hours consumed by individual users, and we have more than 2,800 registered users from 124 countries, and more than 300 of them have conducted projects on the platform. So by accessing advanced services on the platform, using them, publishing results, and also providing feedback to improve the platform. And we see that this community is continuously growing and enriching the feedback that we get from it. Let me spend a few words about the processing service of the GEP. The GEP provides two main features, so data processing services, but also the possibility to the community to integrate their own algorithm on the platform. And the GEP processing services today include basic services, providing full resolution imagery and change detection products for rapid online visualization, as well as advanced services for both optical and SAR data processing. The advanced services include the classic INSAR diachronic analysis, but also advanced INSAR for persistent scatter and small baseline time series, digital surface model generation from satellite optical stereo images, and detection and measurement of horizontal ground motion from optical imagery. As you can see from the picture, the data processing services of the GEP are divided in 3 main categories: data screening, event response, area monitoring, with different characteristics. And the user can select when accessing the platform, can select the category that the best fit its needs, or get access to the full service portfolio by going to the flex option. What is important to mention is that the GEP service offerings is publicly available, and it's also published in the network of resource marketplace, where the user can go there to purchase directly the services by contacting us, or to seek for sponsorship for accessing them. Indeed, it is important to mention this initiative of ESA. The ESA Nord, that is a privileged channel for newcomers to engage with the GEP service offerings, meaning that the user can go to this marketplace and for an initial period request ESA to cover the cost for accessing the GEP services. And this is explained in our blog, in a blog post, and also we are always available to provide support to the user in going through this process. Oh, sorry. Okay. To complete, I will now hand over to the SAT team, that is the science animation team of the GEP. That is a team of researchers and engineers from the Centre National de Recherche Scientifique, they call it Observatoire des Sciences de la Terre in France, and the Aristotle University of Thessaloniki in Greece. And the scientific animation team is supporting us as the GEP operation to best serve the community, but also is providing advice about the contribution of satellite AO data to better understand terrain motion and natural hazards such as earthquakes, accidents, volcanoes, and landslides. And today we have with us Dr. Michael Fomelis, that will give the first presentation, that is a senior researcher and assistant professor in remote sensing and GIS at the Aristotle University of Thessaloniki. And it will be supported by Dr. Jean-Philippe Mallet from CNRS, and also Dr. Florian Provost, again from the University of Strasbourg. After that, we will have Dr. Sayem Nasrullah. Will introduce him after the talk of Michael Fomelis, that will be about INSAR background, online services for time series analysis, and physical and practical examples. If you have any question, you can write in the chat. We will try to provide responses directly there, and then after the presentation, we will also have some time for let's say answering some more let's say complex or articulated question that you may have made. Okay, so Michael, so I hand over to you for your presentation.
So thanks, Fabrizio. So great, good afternoon from my side. I'm Michael Fomelis. So I will discuss today about very shortly and high level about the INSAR principle, about the SAR technique itself, and then the INSAR as an introduction to the services available on GEP for processing by users. So just to mention that this presentation was also prepared with by Florian Provost from EOS CNRS. So starting from synthetic aperture radar, what we call SAR, these are sensors, these are active sensors, which they use their own illumination, they send electromagnetic signal to the Earth and receive it back. Since they are independent of the sun, they can operate day and night. And of course, they have also the capability to penetrate the clouds so you can have cloud-free images for several other applications. And this is one of the main advantages compared to the optical imagery. Once the signal is sent to the Earth, what you receive from what these satellites are capturing, in fact, they are capturing the amplitude and the phase of the signal. Amplitude is exactly this image here, which is showing you the intensity of the backscatter, how strongly the signal comes back to the satellite, and in this way you are imaging the surface of the Earth. Plus, you have a parameter here which is called phase, and it's directly linked to the distance of the satellite to the point of the Earth that you are measuring. For the time being, for simple SAR images, you have a noise if you try to visualize this phase, but then we will see later on how we convert this phase to a meaningful information. Then what needs to be clarified, which is also different from optical data, is that the satellites that are carrying SAR sensors are side-looking. So the signal is not sent from the nadir, but it's side-looking usually from the right side of the satellite, and this is causing a bit of distortion of what you see from the land of the Earth. So you see here, this is a mountain, and you see it a bit distorted. Then, of course, there are several techniques and options how to correct that and to bring it to normal map geometry. The main advantage of the synthetic aperture radar, which is in fact a technique which is simulating a longer antenna to allow you visualize better, have better resolution on the ground, so you can capture smaller objects in your imagery. And this is what is called, in fact, synthetic aperture. Then we can move forward with an idea of SAR, the interferometry. What is done here is that you have you have one acquisition from the satellite, it passes from a specific time, and send the signal, receive it, and capture and record on the image both the amplitude and the phase. Then you have a repeat observation, a second time that the satellite passed exactly from the same location, looking exactly to the same point of the ground, and you have again the amplitude and the phase. If there is a difference, if there is motion between the two scenes, like an object is moving, like in that case the building, you can do what we say SAR interferometry. So you subtract the two phases. So practically you subtract the two distances, and what you get in that case from these noisy phases, you get what we call an interferogram. So each of the cycles, color cycles that you see in a single interferogram correspond to specific millimeters per year, millimeters of motion in the ground. So if you don't subtract, by simulating the topography, you don't subtract the topography, you have, in fact, the mountain, you see the topography. But if you remove the topography, supposing that you have a known information about the topography, then what is left is the differential motion, which is the motion of the ground of the building and so on. This is quite useful for landslide, for earthquake, for coseismic motion, and different applications. Then what usually we do, we cannot interpret easily these fringes, these differential interferograms. The phase is wrapped, so you have each cycle, color cycle correspond to a specific motion, but you can convert that through a procedure which is called phase unwrapping, and what you get is a continuous signal, and then of course that you convert it you convert the depending on the wavelength of the satellite from phase to meters, so you have exactly the displacement of the ground. So moving forward with the idea, this is what we say now conventional differential interferometry, and you can use the idea that the satellites are orbiting the Earth continuously, and of course there is a descending orbit when the satellite goes from the north to the south pole, and when you go up from the south pole to the north pole, then it is ascending mode. So you can, in fact, you are visualizing the same area from two different angles, and we can use these two angles to decompose the motion. So you get one line of sight observation. Lines of sight is exactly the line connecting the satellite to the point of the ground, which is an oblique distance, and you can decompose that into a horizontal east-west motion and actual vertical motion for further interpretation together with other geodetic information like leveling, GNSS, and so on. This is what was the idea of differential SAR interferometry for long period. And then there was the idea of, okay, what if we have several imagery over the same point? So here comes the idea. So you can exploit, in fact, the temporal and spectral characteristic of the interferometric signal over a point where it remains stable. By stable, I don't mean that they don't move, but stable in terms of surface characteristics. So if you do that, you are able to separate points on the ground and not only pixels. So these points usually are objects which are not moving. Here you can see the electrical pillars. These are considered persistent or permanent scatterers, which have a very specific, they remain like that for a long period. Of course, the techniques have been improved since the initial idea of the persistent scatter interferometry, and now we are able also to separate distributed scatterers, which are points which are changing a bit, not much. Of course, there are also areas like the vegetated areas for which usually we don't have information at all because it's the wind, they are moving, they are changing all the time, agricultural areas. So over these land surfaces, we cannot extract deformation or displacement signal for using SAR interferometry. The technique at the time was called persistent scatter interferometry, and you see that you get not pixel but point measurement, and you can decompose these ones into over several buildings, and you can examine the motion of each building block and building separately in time. Here there is an example that you can identify. Also, this is a road network, and you can, of course, here is vegetated area, agricultural land. You don't get any points, but very nicely you can get this road, and you can examine the stability of a bridge over here. Then I mentioned like this persistent scatterers and distributed scatterers. This is different features on the ground, the different ways to extract them, different techniques to extract them. But once you collect a stack of several SAR acquisition over time, supposedly now with Sentinel-1, you can easily reach 300 something, 400 images over a specific area or in Europe. Then you have all these points and you want to process them. And the two main processing approach to do that, it is persistent scatter interferometry, PSI, and the small baseline approaches, which they are called SBUS. Two different approaches proposed by science community. There are also mixtures of them and different ways to process them. But the whole idea of the PSI is that you keep one date stable and you examine the motion compared to the specific date. While for the SBUS approach, you do a network connection of small baselines within the whole acquisitions. Here is the perpendicular baseline, and the temporal baseline. By temporal baseline, we refer to the different time of acquisition of each imagery, and the perpendicular baseline is exactly what we say, the separation in space between the two acquisitions. This needs to be very, very small. And in fact, right now with the Sentinel mission, this is highly controlled up to 120 meters. So you can apply these techniques easily. So different techniques, and the goal of them is to extract average motion of the ground plus the displacement time series. This is just a slide to show that all this started back in '92, where there was the first demonstration from Massonnet about this technology. Then it was revolutionized by Ferretti from Politecnico di Milano in Italy, proposing this new techniques, the PSI, that you get point measurement with millimeter accuracy. And of course, there was a large period where we got the maturity of the techniques, and we can say right now that all these techniques are operational. And you can see this from the number of downloads of imagery from, in that case, from Open Hub of Copernicus. And you see that over time, the number of images downloaded by user is high because exactly they use technique. Once it is operational, and most of the algorithms now provide accurate measurements, you see that we started back in on the 90s with 2, 3, 4 satellites And right now, we have so many missions proposed at different resolution, different wavelengths, different revisit times. So this is right now, it is the golden era of Earth observation related to SAR interferometry and SAR applications. I will not go much on that. I'm available here to reply to your questions, and I will move now to the to what GEP is doing using the INSAR. So GEP has a set of services. We call them services because they are algorithms implemented there for you to use in an easy way. So it's not a DINSAR algorithm or processing, but it's a service because it's able to collect the image for you, process and deliver it to the results. We have several services applying the conventional DINSAR approach, which is very useful for cases of earthquake, for very abrupt motions and strong motion like earthquake or seismic activity, landslide, and so on. We have several of them using only the Sentinel data. Others are using both, also the historical mission of ERS and ENVISAT of ESA, plus the Cosmos Skymet data. And apart from that, we have what we say advanced services, which are offering this mean velocity maps over time, exploiting large data stacks of SAR imagery, plus the displacement time series. This is the case of an earthquake. It was not so strong, so even in that case, the time series could be applied, and you can see the jump due to the earthquake and the post-seismic motion. Three main services are available for that: FastVel, PSBus, and snapping. PSBus and snapping are offering also time series. FastVel gives you only the velocity of the points for the specific observation period. I have two slides now describing graphically more or less the approach that is used for PSBus, in that case from Siena Area in Italy, and this is implemented, and that was shown and discussed extensively in the previous webinar by Florian and Francesca Signa as an application over Mexico. This is the service that we will focus today. It's a PSI approach right now. It is more suited, I would say, for infrastructure monitoring, since there is no averaging in time, and you can get the point of each building. Similarly to the PSBus, we have two versions of the service, one offering medium resolution for wide area application, and the other is for full resolution analysis for building infrastructure monitoring. And this is the cases of the service for the two different versions of it. So here you see an airport here in Thessaloniki, where I'm living, and you get the medium resolution, how it looks, and how it looks the full resolution. Of course, from medium to full resolution, you don't invent point over area that you don't have signal, but you increase the number of points, of course, so you can do more detailed analysis. So the increase of this specific area was the increase was 1,500 times more points. And of course, what you get also the time series, and you can get it from linear motion for even the seasonal motion. So right now we are able to monitor and to extract complicated signals from the SAR imagery over time. This is a case, since we were talking about infrastructure, we did this over the Nile Delta, and we applied the snapping PSI approach. This is the build-up areas over the Nile from the world cover map of ESA, and we extract over every single village there the motion for the period from 2015 until 2020. Then I just wanted to emphasize that apart from having the services there running, one important aspect is to see the consistency of the motion estimates, comparing different services. In this case, it's Cinerea, SBus, and the snapping, and you see that there is more or less a very good consistency between observations. And this is another case over Surabaya area in Indonesia. So don't look too much about the colors, why it's more red here and less red here, because we didn't do any adjustment of the reference points. But the idea is that the patterns are nicely presented in both techniques here. And just to emphasize also the idea that the PSI in general, because it is not average in time, so you don't get a grid of information, but you get the points over the infrastructure or other surface characteristics. You can get, for instance, here, the bridge, it is very well monitored. So this is from my side. I'm happy to respond to your question. Thank you very much, and enjoy the rest of the webinar.
Thank you, Michael. You were very precise in your 15 minutes. Really, congratulations. So I don't see any question in the chat. So I think we can go directly to next presentation and take the questions after that. Let me just introduce. So the next speaker is Dr. Syams Nasrullah, that is a remote sensing expert from the Asian Institute of Technology in Thailand. IT is an independent non-profit institute established in 1959 that provides education, research, development, and technical services primarily targeting the Asian countries. And the Geoinformatics Center at IT provides knowledge and know-how to support the processes of planning and decision-making for sustainable development by integrating spatial information with other conventional methods and tools. IT is a long-term, I would say, collaboration with the GEP that has started in the context of an initiative for support for emergency assistance or rehabilitation and reconstruction in Central Sulawesi, an activity funded by the by the Asian Development Bank. And the presentation of Syams will be about post-earthquake building stability monitoring in Central Sulawesi using persistent scatter interferometry. So Syams, I leave the floor to you for your presentation.
Thank you, Fabrizio. Let me share my screen. Okay, so good evening here in Bangkok. My name is Syams Nasrullah. I think Fabrizio already introduced me. So I'm working in AIT in a center called Geoinformatics Center in Thailand. So I'm going to present our work in Central Sulawesi, Indonesia. So this is title is post-earthquake building stability monitoring. We are using persistent scatter interferometry. So this project is part of the project funded by the ADB and the government of Japan, basically to support the Indonesian government for their reconstruction monitoring activities. So we mainly use geohazard GEP for this work, especially for the SAR-based processing part. And yeah, so yeah, my colleague also, I put it there. So we are working together with Restec Japan, and also the University of Diponegoro, Indonesia, and also Planetech, Italy. So yeah, like I said, basically we are doing this reconstruction monitoring using satellite data in the disaster affected areas. So this is after the 2018 Central Sulawesi earthquake. So one part is actually we are using SAR Sentinel-1 especially, but we also doing processing for optical data. But for this presentation, I'm going to only focus on the SAR-based processing. So a little bit background about the study area, the project area. So here is the project area is Palu. So this is located in the Sulawesi Island in Indonesia. So it is the capital of the Central Sulawesi. And it is not a very big city, I would say. It's a mid city. So it has a population around maybe 300, 400,000 population. And yeah, it is situated in the narrow bay area, so surrounding by the mountain ridges in the east part and also in the western part. And this Sulawesi itself known very region which has a very seismic active region. Not just Sulawesi, actually, I would say the whole Indonesian is very much a seismic active region. So that's why it's called the region of fire. So there are several active fault lines pass through the island. So there's one for Palu-Koro fault line. So from the north to south line, and there's another also in this southeast is Matano fault, and the others, some other also fault line. So in September 28, 2018, so there's a strong earthquake, 7.5 magnitude, that hit the island. So in the northern part of Palu, as you can see here from the map, and then it followed also with the second earthquake with magnitude of 6.1. So this earthquake caused a lot of damage, and it's also triggered actually tsunami in the coastal area, so in the urban area, and also the soil liquefaction. So where the soil lost its strength, so then the building was absorbed to the soil, and also some part landslide. So this is the area that actually we are looking at, and we are working 2 years after the earthquake itself, so in 2021. So our job is supposed to do the reconstruction monitoring for this post-earthquake area. So basically the objective is to provide information on critical infrastructure, building, ground movement, and other information needed to support the reconstruction monitoring after the 2018 earthquake and tsunami. So we are using SBUS in GEP to do this wide area measurement and monitoring, and also the PSI, persistent scatter interferometry, for point measurement, building measurement. And also we do some, we extract also building stability information based on the output from PSI. So you see here the map actually showing the damage after the earthquake. So I think more than 2,000 people died, and a lot of building, a lot of infrastructure destroyed. So, and also you see here in the lower part, the image, you see the liquefaction, where you see the image before the earthquake, and then the image after the earthquake. Then you see this red point is the building that is destroyed after the liquefaction. So there are a lot of damage in this area basically. So we are using, we basically process the central water using GEP. So we are using two services here. One is SBUS and also snapping PSI. But actually we are using the medium resolution snapping PSI because at that time we don't have the access to the full resolution. So yeah, but now I think GEP also already released the full resolution PSI. And we do the process for different time period. So we have pre-earthquake, post-earthquake, but we mainly do the processing, the time series processing for the post-earthquake, starting from we always use the same starting image in October 2018, that is after the earthquake, but then we do the following monitoring for different timeline, like for example in December 2021 and then March 2022 and so on. So basically we are doing every 3 months, we are trying to monitor the situation, the condition, the ground situation. And actually this project also continuation from the previous project. So we have also result from the previous project that measure the displacement before 2022. So we just use those products, so see how we are going to continue the measurement. So so this is the example of the measurement that we did. This is for SBUS in both direction, in descending and ascending. This is for the observation period from October 2018 to March 2022. So you see here the motion in several areas and showing that red color, and this is a subside negative motion, and then also the blue motion, the blue area. And if you can see here the ascending and ascending, this is showing the different, that they highlight the presence of the horizontal movement, horizontal component of the deformation. So this is from SBUS, but then also we are looking at, mainly looking at this PSI. So similar, actually quite confirm the result from SBUS also with PSI. But the different thing is because because the PSI mostly looking at the building, the point location, so it is expected to have much better accuracy in case of PSI. But in SBAS, we are looking more wide area, right? So for our building stability analysis, we are mainly using this PSI product. So we did some evaluation also about the results. We use the GNSS core station in one of station in Palu area. So we are looking at the observation from October 2018 up to August 2022, and yeah, we try to compare with the GPS measurement that is already converted to the loss direction in both descending and ascending. So there are some good correlation, like as you can see from this graph here. And so this is the ground movement monitoring from different time period. This is actually from the previous project, but just to show you that the situation on the area. So in the beginning, this is the situation before the earthquake. So you see that mostly the ground is quite stable. So this is before the earthquake, and then 6 months after the earthquake, that you see that a lot of area that is having a strong motion, like in this area, red area, and also this blue area. And then 3 years, 1 year after the earthquake, so things are getting better. So you have less red area, but still quite strong motion in some part of the area. And especially because as I said, there's a fault line also passing through from north to south direction in this area. So you see a very strong motion in that part of area, and also in this southeast area. And this is the measurement 3 years after the earthquake. So you can see that it is much more stable in that case. Right? So you see also the different velocity that looks like getting much more stable for this area. So we are doing another monitoring for 2022 every 3 months. So as you can see here, actually not much change in terms of the overall ground motion, but it slowly decrease. As you can see here, this is from the descending orbit measurement. This is up to December 2022. And then, yeah, this is looking at another ascending orbit. So you can see here, there's some movement also, there's some motion also in the area. So this is close to the fault line area. And yeah, and this is also, but still also decreasing also, as you can see from this time series map here. So what we do is actually we are trying to extract the building stability information from the PSI. So we are classified into 4 classes: low, medium, and high. And then we are using as a base data is a building footprint from BIG. BIG is the National Geo Information in Indonesia. And then we just simple technique to estimate the closest PSI point value for each building centroid based on the buffer distance. So we are using like, I think, 100-meter buffer distance. Then we classify based on the statistical value for each building. So we'll get this low, medium, and high classification. And this is the result. This is in December 2019. So this is the coming from the previous project actually. So you see here the in the highest level of inspection priority. So where the red color shows the high motion, like in this part of area, in this 3 part of area. So mainly are located in the close to the fault line, but there's also area that's showing a very high motion in the southeastern part. And this is in March 2022, so 3 years after the earthquake. And you see there are less motion in the southeastern part, but there are still motion in the close to the fault line. Yeah, similarly, this is for September 2022. So you see also a similar kind of pattern with the previous month. So the next slide, actually, I'm going to show you some example of the specific location that's showing the information of building stability as well as the ground displacement. So for example, here is the building stability in the resettlement area. So resettlement area for Huntap. So the government already decided several locations for this resettlement area. And then if you look at the picture here, So this is actually the building stability map for each area. And you see that most of the reconstruction area is located in the quite stable area. And then this is another example for the public facility like mosque, big mosque in this area, and also the hospital. So you see the stability also, you can see from here, and you can also check the velocity that is more or less not so much in this location, in this building, and also in this hospital, similar thing also. And then for this another infrastructure, we're also looking at this airport. So you see the airport is also more or less quite stable, so only 0.7 millimeter per year in velocity. And also another infrastructure is dam in Gumbasa. It is also very less motion in that area. So actually in case of airport, you see a lot of points located in the airport, so very nicely you can see. But in some areas very limited, because I think because of course the lack of the coherent object, so then you get less point. So what we do is just estimate the closest location from that building, that our object that we want to observe. And let me go through quickly. So this is another infrastructure bridge, so you can easily but this is only few points actually on bridge. This is one location, and this is in another location. Yeah. And this is a road. So looking at this road that is mainly destroyed because of the earthquake and also because of the tsunami. So you see there are some still movement in this part of the road, and also this part of the road close to the liquefaction areas. And also there are some negative, some subside in this area. And yeah, we also important for looking at this canal, so Gumbasa Canal. So there are a long canal here, so that we are trying to monitor the condition for this area. So this is one segment of the canal, and this is another segment of the canal. So okay, so just one note that I mean, we are using actually medium resolution PSI, but if you use maybe GEP full resolution, you may expect this kind of more point that you will get, right? So then you may have a better estimation on the stability. And yeah, so this is just showing you the difference between medium resolution and full resolution. And when we try to estimate the building stability, also you see that it tends to generalize the building if in medium resolution, if you compare to the full resolution. Okay, so this is actually our website. So if you want to play around and want to check how the displacement, how the building stability, and on top of the map, on top of the image, so then you can go to this website pgo.ait.h.th, and this is open access actually, so you can also try if you want, and not just the SAR product but also the optical product, also you can check the damage status. Just quickly to summarize, to conclude, so the updated ground motion and building stability analysis highlighted the post-seismic deformation decreased significantly with respect to NS from 1 year after the earthquake. So you see that stability actually start to happen even after 1 year after the earthquake. But then we are trying to also continuous update that allow to verify the post-earthquake condition when it will be back to the pre-event condition. And this is also useful for design during the ongoing reconstruction activities. And since we are using this medium resolution, I think to improve the result, it's good to also use the more the high resolution snapping PSI that will provide more dense displacement and velocity points. So I think with that, I will stop my presentation. I think I'm a bit over time. So thank you so much. If you have any questions, you're welcome. Thank you.
Okay, so thanks a lot, Siams. Thanks for your presentation. I see that there are quite some questions, so I would ask Michael and Florian maybe to select those ones that maybe needs an answer in voice. I think there are a few ones also to Siams. So maybe we can start with them and then go to the previous ones. For example, let's see.
Yeah, so basically Michaelis has already answered like most of the question. Maybe one is for Siams, which is from Yunus Mohamed. Could you talk a bit more on how you do the building stability analysis? Is there any several options to do that?
Yeah, thank you. So actually, basically, we are doing a very simple method to estimate this building stability. So we are only looking at the average velocities, and then we try to buffer, so then we can estimate the velocity for each building. There are several other methods also that you can use. Which include more information into the estimation. Like you can use the coherence information. Also, some of the building stability, they use coherence information, and yeah, they are using also some other statistical value, or maybe incorporate with the say for the optical data analysis, so we know where the building that is. So this like basically to calibrate the result. But when I check the our result, actually quite match with the one that using a bit more sophisticated method, I would say. So that's why we are still going with the a bit simple, but I think it's quite okay to do that way. Okay. So I hope that answered the question.
Yeah, I think so. Thank you very much. I don't know, Mohamed, if
I see.
yeah, so he's asking if you had like a threshold somehow like that would differentiate from stable to not stable building. Like what threshold did you use, or how did you estimate the level of stability?
Yeah, I think that is for me, right? Yeah, we use low, medium, and high motion, but that will be depend actually on different area. So it may have different classification threshold. But in our case, we are using the standard with the the difference with the mean. So we using the standard deviation. So for example, for low motion, we are using between 1 standard deviation to -1 standard deviation, and then for medium we are I think we're using 1.5 to -1.5, and then for a medium we are using 2 standard deviation, and then high is above 2 standard deviation. So that is how we do, but I think it will be different for different area. So, and also this is something to note also, this is actually just an estimation on the inspection priority. So it doesn't mean that the building is say dangerous, right? Or it's like fully safe. So this is just a indication that is the motion going on for that particular building, especially in those area. So it may it can be used to do more detailed inspection on the ground. Okay, so with that information, then you have to go to the field and then do more inspection, and then in that high motion area based on our classification, then that is how it's supposed to do. So it's not taking as it is, but need to do more detailed analysis in the ground. Yeah.
Thank you very much. There is one next question, which is you mentioned that you use GPS results convert to loss, but in some slides you also use vertical loss. So the question is, how did you manage the north-south motion in the Palu earthquake that was quite large, and how is and more significant than the up and down motion?
Sorry, can you repeat the question?
So the question is like the Palu earthquake was mostly north-south motion. So how significant is your up and down motion to compared to this motion?
Yeah, so I think based on the analysis, actually, we also see the presence of horizontal and a vertical motion. So in case of vertical motion, I think in case of radar, you cannot estimate the north-south direction. You can only see the east-west direction because of the way the satellite, operate, right? And then you can also the vertical direction. So actually for building analysis, we are consider both ascending and descending direction. So yeah, so we are looking in those direction because we understand that there's also this vertical and horizontal movement in that area. So yeah, I'm not sure if that is answer the question. Yeah.
Okay, thank you. Yeah, I guess with INSAR it's difficult to evaluate the north-south motion, as you said. There is one question maybe more for Michaelis, which is, do time series products include epoch-specific uncertainties? I don't know.
Yes. So I try to reply also that for the multi-temporal time series approaches, the measures of accuracy is the temporal coherence of the point. So it's a qualitative measure, plus the sigma of the motion that you measure. So the uncertainty in the average velocity. There was a very nice question from I think David Small, saying, what about if there is unwrapping errors, which they might occur, of course, for specific area or specific points. These ones, usually you see them as very, very strong spatial patterns, which are deviate from the locals. But also you can see them in the time series. So you see motion which is completely non-regular or jumps and so on. So I said also that there are ways that there has been proposed recently approaches for solving these unwrapping errors. Of course, you have some ways to do that without going too deep. So for instance, the service is proposing the split of the area into small tiles in order to parallelize processing 4x4. If you change these tiles, make it 2x2, 6x6, whatever, you are changing the unwrapping procedure also inside, because you take other areas to unwrap. So if you have such a problem, you can change also the way the procedure is run in the service, so you can ensure that your results are good. This is also what we do when we see a very strong signal and we are not sure if this is a signal or something else. There is nothing in the time series to indicate that this is an unwrapping error. We did just yesterday that with Florian. So we said, okay, we will do with a different unwrapping window and what in the tiles of the service. And then if you get exactly the same solution, then you are more convinced. And of course, what you can do again is you process independent data sets. So if you do ascending and descending, and this pattern is there for the two data sets, then you are more sure that this is not an unwrapping error and there is a signal. If you see something which is not, it appears only on a specific time, specific data set, then the probabilities of an unwrapping error are higher. I hope I gave some answers and not complicate more.
Yeah, thank you very much. So maybe one last question, because we are like reaching the end of the webinar. It was about the resolution of the full service, like full resolution service. He's asking, well, what kind of information do you want more, David Vidal and Torres? Maybe I can send you a link to the tutorial so it will be easier. Maybe you can ask a last question, Michaelis, about.
Yes, for performing PSI, could we do APS estimation on GEP And what kind of standard condition of coherence image or other that we can excuse and should APS estimation or not. So there is an option to apply the atmospheric filtering, the linear atmospheric filtering, and you have an option also to change the window for this atmospheric filtering. So you can try to apply it, but you need also to be careful because sometimes this APS filtering are smoothing a bit the signal, the temporal signal as well. How to increase accuracy of S-bus at hill mountain. So there is no way to increase the accuracy of the INSAR measurements. What we usually say that if you have a very strong motion, even 1 year of observation could be enough to extract this motion. But if when the motion is going lower, lower, and it's very almost negligible to get accurate measurement of such small motion rates like 2 or 3 to be sure that this is the value, you need to increase the observation period. This is exactly the same as other geodetic approaches like GNSS. So you need at least 3 years of observation to make sure that your estimates are correct. And just to reply, last question, the 3D motion from INSAR, there is a service designed already and it's being integrated on GEPs. Soon you will have it, which is reading the ascending and descending observation from the snapping service and provide you with a decomposition, the east-west and the up component.
Okay, so I think we have to close also now as we are in our time. So I thank you the presenters, and I hope for all participants this has been interesting. Just to conclude, we will let's say share the recording and material in the next days. This will be announced on the blog of the GEP and via Twitter, so you will be able to find it. And then if you have any question or request, just contact us and we will try to reply very quickly. So thanks again, and I think we can close here. So thank you and bye-bye. See you to the next webinar.
Thank you all for your participation. Thank you.
Bye.